Well, hello guys, Mr. G here with another question from 2016 June examination done at the Northern Cape at the Free State provinces. This question is Newton's law, and before we continue, please don't forget to subscribe for the channel so you can get all the notification videos and worksheet. Now, this question says a block of mass 4 kg is connected to another block of mass 2 kg by a light and extensible string. The system is pulled up a rough plane inclined at 30 degrees to the horizontal by means of constant force of 73,8 Newton parallel to the plane as shown in the diagram below. And here is the picture of the question. The magnitude of the kinetic frictional forces on the 4 kg block is 20 Newton. The coefficient of kinetic friction between the 2 kg block and the inclined plane is 0,589. Define frictional force in what? Okay, and the frictional force is the force that opposes the motion of an object and which acts parallel to the surface. That is what we call frictional force. Let's go to question 2.3. Now, question 2.3 says, state Newton's second law in words. So, when a resultant force acts on an object, the object accelerates in the direction of the net force. At an acceleration, the acceleration is directly proportional to the net force and inversely proportional to the mass of the object. That one is the Newton's second law in words. In symbol, we'll say that acceleration is directly proportional to net force and the acceleration is inversely proportional to the mass of the object. The formula for this law is F net is equal to the product of ma. If from here you rearrange this one to calculate acceleration, then we'll get that the acceleration is equal to F net divided by mass. And from here, guys, we can deduct that law. The formula is given to you so you can use it to remember the law if you think you are going to forget. The acceleration is directly proportional to the F net and inversely proportional to the mass. Okay, so let's go to question 2.3. Question 2.3 said, draw a free body diagram with a label showing all the forces acting on the 4 kg block as it moves up the incline. Please be mindful of the following. You may not include components of the forces in your diagram. You may not use numbers as label. So, in this case, we're going to draw the free body diagrams on this side here. On this side here, question 2.3 is very simple. Here is the object. Now, what forces are acting on that object? They want for the 4 kg block. We're going to start with the forces that we can actually see easily. For instance, we have here, parallel to the surface, we have the applied force. They say not numbers, so you cannot write 73,8. This one is applied force. What are the forces acting there? There is normal perpendicular to the surface. Here is normal because there is a surface acting on that object straight up or perpendicular to it. There is weight, all the weight straight down, that is weight. There is tension to the back. There is tension, but there is also friction on that block straight along the line with tension. Yes, I'm going to do it a little bit longer. It doesn't need to, it could be short or long. It does not really matter in this case. So this is frictional force, and those are the forces acting on the 4 kg block. If you count, you have 1, 2, 3, 4, and 5 forces, and here there are 5 marks. So that is the free body diagram they want. I always told you when these 4 questions, you cannot add the components or even the axis. Now calculate the magnitude of the kinetic frictional force on the 2 kg block. So we're going to look for the frictional force, but to do that we're going to a new page and we are going to redo or do a free body diagram for the 2 kg block, but we are going to do a free body diagram with everything that we need. Now here's the free body diagram, but I did not include the components, so we're going to add the components of the weight. remember weight must be projected to the y-axis, which is this one. This one is weight in the y-axis, guys. This one has been done in another question. Remember, this angle is the same as the angle of inclination that it was here. The angle of inclination is 30 degrees. So remember that one. So now if you use that one, weight in the y-axis is equal to weight multiplied by the cosine of 30 degrees, in case we need it. We're going to need it a little bit later. And then this one here will be also projected to the x-axis, and here you will have weight in x, but it's also going to be here if you add the vectors properly. That one is weight in the x-axis, which is equal to weight multiplied by sin 30 degrees, guys. Okay, so now they're looking for frictional force. Frictional force is equal to the kinetic coefficient of friction multiplied by the normal. Let me show you. The formula is here. Here is the formula for, no, this one is maximum static frictional force, sorry, on this side. This one is the kinetic frictional force. There is the formula, okay? Well, guys, for this part, we know that the kinetic coefficient of friction is known by us and is equal to 0.589. That is the kinetic coefficient of friction. And then the normal force, we don't have the normal force. And I show you many times how to calculate the normal force. All you have to go is to the y-axis. In y-axis. And then in y-axis, I am going to apply Newton's first law. F net is equal to to 0, sorry. Equal to 0. And then the forces, they are going to be normal minus weight in the y-axis is equal to 0, then normal is equal to weight in the y-axis, and then this one is equal to weight multiplied by the cosine 30 degrees, and then weight is mass multiplied by acceleration due to gravity, mass acceleration due to gravity, cosine 30 degrees. And if you substitute, I'm going to substitute on this side here. Then the normal is 16.97 Newton. And then this one can be substituted there in the formula for frictional force. So when we substitute here for friction, we have that is equal to 0.589 multiplied by 16.97, and then the final answer for friction is going to be 10 Newton. So the answer here is 10 Newton, guys. This is the answer of the first calculation of this question. Frictional force is 10 Newton. Okay? So let's go to the next question. The next question is question 2.5, and they say calculate the tension in the string that connect the two blocks. Now for this one we have to work simultaneous. So for this one we want to work separated for both objects. The free body diagram for question for the 2 kilogram block was done previously here, so I just copy and paste it there. And the free body diagram for the 4 kilogram block, we're just going to do it. Everything is there except for the component. I'm going to project here, and then we have here in the y-axis weight in white. Same story, guys, as before, but it's another object. And if we project to the x, we have in here in the x, we have in now the weight in x-axis. So we're going to be using both objects simultaneously. Now I want you to notice something. The tension is in the x-axis, so we are going to be using the x-axis, Newton's law in both of the axes for both objects. So we're going to be using Newton's second law, F net equal to mass multiplied by acceleration for both objects in the x-axis. In x-axis, okay? So in x-axis for the 2 kilogram block, what we have tension minus frictional force minus weight in x is equal to the product of ma. If we go to the 4 kilogram block, we have a little bit more. We have the applied force minus tension minus frictional force minus weight in the x-axis equal to ma. And then it's just to solve all this one here. Right? Now the frictional force was calculated, but the weight in the x-axis was not calculated there. So we have to calculate the weight in x here, and we have to calculate the weight in x there, but it's quite simple. So we are going to first calculate those two. And the rest is to substitute everything on the equations that have the tension there. And guys, here is equation 1. We have two unknown, so we cannot carry on. We're going to stop there and call this one equation 1. And we're going to work now with the second block. So when we substitute here for the second block, and once more we have a second equation, we cannot carry on because we have two unknown. Now all we are going to do is to add those two equations. So let's add the two equations, guys. When we have the acceleration, we are going to substitute in either equation 1 or equation 2. We are going to use equation 1. So you have, and the final answer is 24.6 Newton. That is the tension in the string, guys. This one is this equation 2.5. This is the way I do it. In South Africa, they like to do it simultaneously and work with two equations, so try to do it like this. Now, question 2.6 said, the system is pulled up the rough incline once more, but this time the two blocks are swapped as indicated below. How will this influence each of the following? Choose your answer from decrease, remain the same, or increase. The acceleration of the 2 kilogram block. Okay, if they swap the blocks and they pull with the same applied force, nothing will change in terms of acceleration. The acceleration will remain the same. The force of friction on the 4 kilogram block will also not be affected because it doesn't matter which block is moving at the front and which one is moving at the back, as long as they're still connected and moving at the same acceleration and so on. So this is also remaining the same. And the final one is the tension in the string. And now I wanted to look something here. Now everything stays, many things stays the same. However, when you calculate the tension, the applied force that you see here will be applied to the 2 kilogram blocks and not to the 4. And because of that, when you do all these calculations once again, you will determine that the acceleration, the tension of the blocks is a little bit greater. So it does in actual fact increases. So what I recommend you is to redo calculation with this new situation and you will lead to the answer. So the answer here is increase. That is the answer. And guys, this is the end of this question. I hope it helped. It's a good question to practice. It's Newton's law of motion. It's a lot of marks for this question. It is going to be a lot of marks in the new examination as well at the end of the year. But thank you for watching. Subscribe for the channel. I'll see you next time. Mr. G here.